Chapter 30: Inductance, Electromagnetic Oscillations, and AC Circuits. We will cover these units in this chapter: mutual inductance, self-inductance, energy stored in a magnetic field, LR circuits, LC circuits and electromagnetic oscillations, LC circuits with resistance, LRC circuits, AC circuits with AC source, LRC series AC circuits, resonance in AC circuits, impedance matching, three-phase AC. Section 1. Mutual inductance. A change in current in one coil will induce a current in the second coil. EMF in the second coil is equal to minus M21 times the derivative of current in the first coil over time, and vice versa. Note that the constant M, known as the mutual inductance, is the same. M21 is equal to N2 multiplied by phi 21 over I1. Unit of inductance is the Henry. 1 Henry is equal to 1 volt times second over ampere and is equal to 1 ohm times second. A transformer is an example of mutual inductance. So on the right we see two coils in which current I1 in coil 1 is causing an induction of EMF in the second coil. Let's look at problem number 4 in the book as an example. A long straight wire and a small rectangular wire loop lie in the same plane, as shown in figure 30-25 and is shown here. Determine the mutual inductance in terms of L1, L2, and W, and assume the wire is very long compared to L1, L2, and W, and that the rest of its circuit is very far away compared to L1, L2, and W. So to solve this problem, we have to use equation 30-1 for the mutual inductance, and we have mutual inductance equals to flux over current. For the magnetic flux, we have to use equation 28-1. That is given by the integral L1, L2, mu naught I1 over 2 pi r W dr, which is the area, dA. And that can be simplified as M equals mu naught W over 2 pi natural log of L2 over L1. Section 2. Self-inductance. A change in current in a coil will also induce an EMF in itself. The EMF induced is equal to minus N, the derivative of the magnetic flux over time, and is equal to minus L times the derivative of current over time. Here, L is called the self-inductance and is given by the number of loops, N, multiplied by the magnetic flux phi B divided by current I. As an example, I'll look at problem number 8 in the book. An air-filled cylindrical inductor has 3200 turns and it is 2.5 centimeter in diameter and 28.2 centimeter long. A asks, what is its inductance? And B asks, how many turns would you need to generate the same inductance if the core were iron filled instead? Assume the magnetic permeability of iron is about 1200 times that of free space. From example 30-3, the inductance of a solenoid is given by mu naught N squared A over L. So, let's plug in the values for part A. The inductance of the solenoid is given by 4 pi times 10 to the power minus 7 Tesla meter over ampere times 3200 is capital N squared times pi. The radius is 0.0125 meter squared divided by 0.282 meter. And that gives us 0.02240 Henry, almost 0.022 Henry. For part B, we apply the same equation again, but now this time we solve it for the number of turns. So if we say L is equal to mu naught N squared A over L, number of turns would be equal to the square root of L times inductance over mu naught A. And if you plug in the values, you have the square root of 0.02240 Henry multiplied by 0.282 meter divided by 1200 multiplied by 4 pi times 10 to the power minus 7 Tesla meter over ampere multiplied by pi times 0.0125 meter squared. Number of turns will be given as 92 turns. Section 3. Energy is stored in a magnetic field. Just as we saw that energy can be stored in an electric field, energy can be stored in a magnetic field as well, in an inductor, for example. Analysis shows little u as the energy density is given by 1/2 magnetic field B squared divided by mu naught. Okay, we'll look at problem number 16 in the book as an example. What is the energy density at the center of a circular loop of wire carrying 19 amp current if the radius of the loop is 28 centimeter? So to solve this problem, we use equation 30-7 to calculate the energy density with the magnetic field. Also look at example 2811 for the magnetic field of circular loop. So energy is equal to 1/2 B squared divided by mu naught. And from that example, B is equal to mu naught I over 2R. Let's combine these two together. So density of the magnetic energy is equal to 1 over mu naught I over 2R squared. It simplifies as mu naught I squared over 8R squared. If you plug in the values, UB is equal to 4 pi times 10 to the power minus 7 Tesla meter over amp times 19 amp squared divided by 8 times 0.28 meter squared. And that gives us 7.23 times 10 to the power minus 4 joule per meter cube, which is the density of the magnetic energy. Section 4. LR circuits. A circuit consisting of an inductor and a resistor will begin with most of the voltage drop across the inductor, as the current is changing rapidly. With this, the current will increase less and less until all the voltage is across the resistor. So, in the figure on the right, we'll have a circuit containing a battery indicated with V0, and that is connected with a resistor R, and also an inductor indicated with L. As the switch has been on and the voltage is applied, the current through this series of R and L will gradually go up from 0 to V0 over R an infinite time. So the sum of the potential differences around the loop gives L times di over dt, which is the EMF induced in the inductor, plus R times I, which is the Ohm's law for the resistor, is equal to V naught, the total voltage from the battery. Integrating gives the current as a function of time, and it's given by I equals V naught divided by R multiplied by 1 minus exponential of minus t over tau. The time constant of an LR circuit is tau equals L divided by R. So after a while, if the circuit is then shorted across the battery, the current will gradually decay away as the energy stored in the inductor will be given out into the circuit, but the current will decay exponentially as given with this equation. I equals I naught times e to the power minus t over tau. Alright, I'll look at problem number 22 in the book as an example. How many time constants does it take for the potential difference across the resistor in an LR circuit, like the one shown down here, to drop to 2% of its original value after the switch is moved to the upper position, removing V naught from the circuit? We know the potential difference across the resistor is proportional to the current. So we set the current I equals I naught e raised to the power t over tau to be equal to 0.02, which is 2% of the maximum current. So let's solve this equation for time t. I naughts will cancel out, and if we take the natural log of both sides, we have minus t over tau equals natural log of 0.02. Therefore, time t is equal to minus tau natural log of 0.02, which is almost 3.9 tau. So how many time constant? 3.9 times the constant tau. Section 5. LC circuits and electromagnetic oscillations. An LC circuit is a charged capacitor shorted through an inductor. A charged capacitor with the capacitance C is shortened with an inductor. After the switch is being closed, current I will flow through the inductance from the charged capacitor. So, by summing the potential drops around the circuit, we can find the differential equation for charge Q over time. So we have the second derivative of charge over time plus the charge divided by L times C should be equal to 0. This is the equation for simple harmonic motion and has the solutions of Q equals Q naught, initial charge in the capacitor, multiplied by cos omega t plus phi. Substituting shows that the equation can only be true for all times if the frequency is given by omega equals 2 pi f, should be equal to the square root of 1 over L times C. The current is sinusoidal as well. Current is equal to omega times Q naught sine omega t plus phi. And that is equal to I naught times sine of omega t plus phi. Therefore, the charge and current are both sinusoidal, but with different phases. So here we see the charge on the capacitor is oscillating in the inductor. So the charge and capacitor goes back and forth between the capacitor and inductor, but the current will have a different phase with respect to the charges, and that is 90 degrees off. So when the charge is the max, we have minimum current. When the current is max, we have zero current in the capacitor, and this cycle will continue. However, the total energy in the circuit is constant. It oscillates between the capacitor and the inductor. So the total energy is equal to the energy in the inductor plus the energy in the capacitor, and we represent it by UE plus UB. So U is equal to 1/2 Q squared divided by C plus 1/2 L times I squared. That can be written as Q naught squared over 2C multiplied by cos squared omega t plus phi plus sine squared omega t plus phi. This value becomes 1, and the total energy will be equal to Q naught squared divided by 2 times C. So in the cartoon down in this page, you'll see the energy is oscillating between the electric energy and magnetic energy, shown with the red and blue lines respectively. Alright, let's look at problem number 30 in the book as an example. At t equals 0, let Q equal Q naught and I equals 0 in an LC circuit. A asks the first time when the energy becomes shared equally by the inductor and the capacitor, what is the charge on the capacitor? And B asks how much time has elapsed in terms of the period t. So for part A, we know that when the energy is equally shared between the capacitor and the inductor, the energy stored in the capacitor will be 1/2 of the total initial energy in the capacitor. We use equation 24-5 to write the energy in terms of the charge on the capacitor and solve for the charge when the energy is equally shared. So we have Q squared divided by 2C is equal to 1/2 Q naught squared over 2C. What is the charge? Square root of 2 divided by 2 times Q naught. For part B, we insert the charge in equation 30-13 to solve it for time. So we have root 2 divided by 2 times Q naught is equal to Q naught cos omega t. And let's solve it for time t is equal to 1 over omega cosine inverse of the square root 2 divided by 2. That gives a pi over 4 value. Instead of omega, we can say 2 pi over t, and cosine of pi over 1 over pi, and cosine inverse of root 2 divided by 2 is pi over 4. Let's plug in this value. So we have t over 2 pi multiplied by pi over 4. That gives us t over 8. Section 6. LC oscillations with resistance, LRC circuits. Any real non-superconducting circuit will have resistance. So here we have an LC circuit which contains some resistance and should be taken into account. So here we have a capacitor C connected to an inductor L, and we have some internal resistance into the circuit represented with R. When the switch is connected, the LRC circuit will be formed. Now that we have the voltage drop around the resistor, the total voltage drop around the circuit will be L times the second derivative of charge over time in the inductor plus RI, which is the Ohm's law, and instead of I we can say dq over dt, the derivative of charge with respect to time, plus Q over C, that's the charge stored in the capacitor, and total is equal to 0. The solutions to this equation are damped harmonic oscillations. The system will be underdamped for R squared less than 4L over C and overdamped for R squared larger than 4L over C. Critical damping will occur when R squared is equal to 4L over C. This figure shows the three cases of underdamping. Case A, overdamping, curl C, and critical damping, curl B, when R squared is equal to 4L divided by C. The angular frequency for underdamped oscillations is given by omega prime is equal to the square root of 1 over L times C minus R squared divided by 4L squared. The change in the circuit as a function of time is given by Q equals Q naught times e raised to the power minus R over 2L times time t multiplied by cos omega prime t plus phi. Let's take a look at problem number 32 as an example. In an oscillating LRC circuit, how much time does it take for the energy stored in the fields of the capacitor and inductor to fall to 65% of the initial value? I have to remind you, when we were driving equation 30-16, we said the total energy, U, as the sum of the electrical energy and magnetic energy. Also, the charge was given by equation 30-19, and we can solve the time when the energy is 65% of the initial energy. So let's write down U is equal to charge squared over 2C for the electric energy plus L I squared over 2 for the magnetic energy. And let's plug in the values from equation 30-19 for the charge as Q naught squared e to the power minus R over L t divided by 2C cos squared of the quantity omega prime t plus phi plus Q naught squared divided by 2C e to the power minus R divided by L times t sine squared of the quantity omega prime t plus phi. So the constant value of Q naught squared divided by 2C e to the power minus R over L times t, and we have cosine squared of omega prime t plus phi plus sine squared of omega prime t plus phi. This value is equal to 1 and it simplifies as Q naught squared over 2C e to the power minus R t over L. So the question is asking how much time it takes to reach to 65% of the total energy, and we say 0.65 Q naught squared over 2C, that's 65% of the total energy, is equal to Q naught squared over 2C e to the power minus R t over L. After canceling the constant values and equal values, you can solve it for time t as minus L over R natural log of 0.65. It's almost 0.43 L over R, and we call L over R as tau. Section 7. AC circuits with AC source. Resistors, capacitors, and inductors have different phase relationships between current and voltage when placed in an AC circuit. The current through a resistor is in phase with the voltage. Here we have an AC source connected to a resistor. The AC source will generate an AC current which is in phase with the phase of AC voltage. But if we connect this AC source to an inductor, The voltage across the inductor is given by V equals L times the derivative of current with respect to time, and that is equal to minus omega times L times I naught times sine of the quantity omega t. Or V is equal to omega L I naught times cosine of quantity omega t plus 90 degrees, and is equal to V naught cosine of omega t plus 90 degrees. Therefore, the current through the inductor lags the voltage by 90 degrees. And here's the current in the inductor, which lags 90 degrees from the voltage. The voltage across the inductor is related to the current through it by V naught is equal to I naught times XL for the maximum or RMS values, not for at any instant. The quantity XL is the inductive reactance and has units of ohms. XL is equal to omega times L and is equal to 2 pi times frequency F multiplied by L. In another scenario, when the alternating voltage is connected to a capacitor, the voltage across the capacitor is given by V equals I naught times 1 over omega c times cosine of the quantity omega t minus 90 degrees, and is equal to V naught times cosine of omega t minus 90 degrees. Therefore, in a capacitor, the current leads the voltage by 90 degrees. So we have the red AC voltage, and the current is leading the voltage by 90 degrees, as represented with the blue line. Also, the voltage across the capacitor can be related to the current through the relation as V naught equals I naught multiplied by XC, and XC quantity is called the capacitive reactance, and just like the inductive reactance, has the unit of ohms. It's given by 1 over omega times C, which is equal to 1 over 2 pi times frequency F times capacitance. The figure here shows a high-pass filter which allows an AC signal to pass but blocks the DC voltage, and also a low-pass filter which allows the DC voltage to be maintained but blocks the high-frequency fluctuations. So here on the left we have a high-pass filter which blocks the DC voltage and allows the high-frequency signal to pass from circuit A to circuit B. We have a low-pass filter which blocks the AC signal but lets the DC voltage to pass through the circuit. Alright, at this point I look at problem number 40 in the book as an example. What is the reactance of a well-insulated 0.03 microfarad capacitor connected to a 1.6 kilovolt RMS 720 Hz line? What will be the peak value of the current? So the reactance for this circuit can be found from equation 30-25, and it's given by XC is equal to 1 over 2 pi F times capacitance. Let's plug in the values. 1 over 2 pi 720 Hertz multiplied by 3 times 10 to the power minus 8 farad. That gives 7,368 ohms, almost equal to 7,400 ohm. For part B, we can find the peak value of the current from the Ohm's law. It's given by peak value of current is equal to root 2 times the maximum current. It's given by root 2 Vrms divided by the reactance, and gives root 2 1600 volt divided by 7368 ohms. and that gives 0.31 amps. Section 8. LRC series AC circuit. Analyzing the LRC series AC circuit is complicated, as the voltages are not in phase. This means we cannot simply add them. Furthermore, the reactances depend on the frequency. We calculate the voltage and current using what are called phasors. These are vectors representing the individual voltages. Here, at time 0, the current and voltage are both at maximum. As time goes on, the phasors will rotate counterclockwise. You can see here, I0 is given with the blue vector, and it's in phase with the voltage across the resistor. We have the voltage across the inductor is VL0, and we have the voltage across the capacitor is VC, and it's given by I0 times the reactance of the capacitor. Sometimes t later, the phasors are rotated counterclockwise with the angular frequency omega. So you see the current I0 and the voltage across the resistor are rotated by omega times t. So does the voltage across the inductance and the voltage across the capacitor. At various times, the voltages across each device are given by the x component of each and the current by its x component. The current is the same throughout the circuit. We find from the ratio of voltage to current that the effective resistance, called the impedance of the circuit, is given by Z equals the square root of R squared plus reactance of the inductor, XL, minus the reactance of the capacitor, XC squared, and it's given by, and can be written as, the square root of R squared plus omega times L minus 1 over omega times C squared. The phase angle between the voltage and the current is given by tan phi is equal to the ratio of VL0 minus VC0 divided by VR0. It's given by I0 times XL minus XC divided by I0 times R. I's cancel out, and we will have XL minus XC over R, or cos phi is equal to VR0 divided by V0, and it's equal to I0 times R divided by I0 times Z, and it's equal to resistance R divided by impedance Z. The factor cos phi is called the power factor of the circuit. Alright, let's look at a couple of examples. First, we look at problem number 46 in the book. Determine the resistance of a coil if its impedance is 275 ohm and its reactance is 145 ohms. So we use equation 30-28C. When there is no capacitive reactance, Z impedance is equal to the square root of R squared plus the reactance of the inductor, X sub L squared. Solve it for R is equal to Z squared impedance minus X sub L squared. Plug in the numbers. R is equal to the square root of 275 minus 145 squared, and that is simplified to 234 ohms for the resistance. As another example, I look at problem number 56 in the book. An LR circuit can be used as a phase shifter. Assume that an input source voltage V equals V0 times sine of the quantity 2 pi ft plus phi is connected across a series combination of an inductor L equals 55 millihenry and resistor R. The output of this circuit is taken across the resistor. If V0 is equal to 24 volts and F is equal to 225 Hertz, determine the voltage of R so that the output voltage VR lags the input voltage V by 25 degrees. Compare as a ratio of peak output voltage with V0. Solve this problem. We use equation 30-23b to calculate the impedance of the inductor. Then we set the phase shift in equation 30-29a to 25 degrees and solve it for the resistance. We calculate the output voltage by multiplying the current through the circuit from equation 30-27 by the inductive reactance from equation 30-23b. Okay, first, the reactance from the inductor is equal to 2 pi f times L, 2 pi times 225 Hertz times 0.055 Henry, and that is giving us 77.75 ohms. The phase shift tan phi is equal to XL over R. So we can solve it for R as XL over tangent phi, and we have 77.75 ohm from reactance for the inductor divided by tangent of 25 degrees. That gives us 166.47 ohm, which is almost 170 ohm. Now to compare the peak output voltage, we say V output divided by V0 is equal to VR over V0. And we know the maximum output voltage is across the resistor, VR, is given by the Ohm's law, IR, divided by IZ. I cancels out and we have R divided by Z, 166.7 ohm divided by the square root of 166.7 ohm squared plus 77.75 ohm squared. And that gives us 0.91. So this means that V output max is equal to 91% of the initial voltage. Section 9. Resonance in AC circuits. The RMS current in an AC circuit is given by Vrms divided by impedance Z, and is equal to Vrms divided by the square root of R squared plus omega L minus 1 over omega C squared. Clearly, IRMS depends on the frequency. We see that IRMS will be a maximum when the reactance for the capacitor is equal to the reactance of the inductor, and the frequency at which this occurs is omega naught equals 1 over the square root of L times C. F naught is equal to omega naught over 2 pi is called the resonance frequency. Here we have a graph of IRMS with respect to different frequencies for two values of small r and larger R resistance. So you can see it becomes larger values for smaller values of resistance, and we have less IRMS values for larger resistances. Alright, now let's take a look at problem number 60 in the book as an example. The frequency of the AC voltage source, peak value V0, in an LRC circuit is turned to the circuit's resonance frequency F0 equals 1 over 2 pi times the square root of L times C. A. Show that the peak voltage across the capacitor is Vc0 is equal to V0 times T0 over 2 pi times tau, where T0 is equal to 1 over F0 is the period of the resonance frequency, and tau equals R times C is the time constant for charging the capacitor C throughout the resistor R. B. Define beta as T0 over 2 pi times tau so that Vc0 is equal to beta times V0. Then beta is the amplification of the source voltage across the capacitor. If a particular LRC circuit contains a 2 nanofarad capacitor and has a resonance frequency of 5 kHz, what value of R will yield beta equals 125? For part A, the peak voltage across the capacitor is the peak current multiplied by the capacitive reactance. So we say XC multiplied by I0 as the peak current. Let's plug in the values. For XC, we say 1 over 2 pi FC. I0 is equal to V0 over R. It's equal to V0 2 pi CR 1 over F0. And this is equal to V0 2 pi tau multiplied by the period T0. For part B, beta is equal to V peak over V0, and from part A, we found that Vp over V0 is equal to T0 over 2 pi tau, and beta should be 125. Instead of T0, we have 1 over F0. So we have 1 over 2 pi F0, and instead of tau, we have R times C. And this is equal to beta. Therefore, R is equal to 1 over 2 pi F0 beta C. Let's plug in the values. 1 over 2 pi. Frequency is 5 times 10 to the power 3 hertz. Beta is 125, and capacitor is 2 nanofarad, and that simplifies to 130 ohms. Section 10. Impedance matching. When an electrical circuit is connected to another, maximum power is transmitted when the output impedance of the first equals to the input impedance of the second. The power delivered to the circuit will be a minimum when the derivative of power over time, dp over dt, is equal to 0. This occurs when the total resistance in circuit 1 is equal to total resistance in circuit 2. R1 equals R2. Section 11. Three-phase AC. Transmission lines usually transmit three-phase AC power, with the phases being separated by 120 degrees. This makes the power flow much smoother than if a single phase were used. And here we have AC voltages with three different phases, V1, V2, and V3, separated with 120 degrees. Summary of Chapter 30. Mutual inductance E2 is equal to minus M multiplied by di1 over dt, and M21 is equal to N2 multiplied by phi21 divided by I1. Self-inductance E equals minus N times the derivative of magnetic flux phi with respect to t, time, equals to minus L times the derivative of current with respect to time. L is defined as N times phi divided by I. Energy density stored in magnetic field is given by 1/2 B² divided by mu naught. In LR circuit, I is equal to V naught over R multiplied by 1 minus e raised to minus t over tau, where tau is L divided by R. Inductive reactance, XL, is given by omega times L, which is the same as 2 pi f multiplied by L. Capacitive reactance, XC, is equal to 1 over omega times C, and is equal to 1 divided by 2 pi f times C. In LRC series circuit, Z impedance is equal to the square root of R squared plus X sub L minus X sub C squared. Resonance in LRC series circuit is given by omega naught, the square root of 1 over LC.